Hello, everyone. So in this video, we'll talk a little bit about variance and the standard deviation of a data set. So before we get started on here, let's just say what we're aiming at with this and with ranges. So the idea is we want to quantify or maybe essentialize. To quantify means assign a number to measure to the let's say to the spread. Want to quantify the spread of the data or a data set. And what does that mean? The idea is, okay, you can have sort of several, I mean, data sets can be very complicated, right? You can have a lot of, you can have them completely spread out evenly. You could have them all clustered around really close to their average. Um, you could have it so that there's a bunch over on one side and a bunch on the other side. So there's a lot of different ways that the data could kind of be laid out. And we'd like to say, okay, how can we see, can we assign a number that tells us that the data is really kind of spread out or not really spread out? And the answer is to some extent, yes. Um, and it has to do with these two notions of variance and standard deviation. It also has a little bit to do with range. If you think about it, range is telling you sort of the width of your data in some way, or in the interquartile case, the width of the middle 50% of your data. Okay, so how do we do this with variance though, um, and with the and with standard deviation? Well, I'm going to give three data sets. We'll just use an example to illustrate these data sets. So one will just be sort of evenly spaced data set, the even numbers from 0 to 10. I'll take the same number n. I mean, in other words, so here I have 6 data points, and I'll also do another 6 data points. This one I'll imagine is just the number 5, the average, over and over and over again. So I can have multiple times the number of, well, I can have a number multiple times. And then I'm going to do sort of another extreme. I'm going to have, you know, all of the first three to be 0 and all of the last three to be 10. Okay, so these are three data sets. And now what I want to comment here is that if you count the average, of the data sets, well, I get 5 here, or the mean, either one. I get 5 here, and I get 5 here. So the average that you get for these three different data sets is the same. And so you don't really, this doesn't really tell you, I mean, you're knowing the average doesn't really tell you sort of how that data is spread out. And indeed, here, if you kind of draw a number line, you sort of have this evenly spaced data. Um, in the second case, you just have all of the data clustered right around, uh, right at the average. Maybe I'll draw little circles at the data points. And then the final one, you have sort of a dumbbell kind of scenario where you have three kind of sitting on one side and then three on the other. So they're sort of kind of spread out in a way, um, like so that there's more extremes at the ends. All right, so now let's introduce these notions of variance. Before we do that, we need to compute this sort of deviation from the mean. So for each of our data points, we want to compute the deviation from the mean. And what is that? We just take so this is, we take the data point, and we subtract the average. So this is going to be, so for data point uh, X, this is This is x minus the average. Okay, so let's do it for our three different cases. In the blue data set, we have -5 because we're taking 0 minus 5. Here we have 2 minus 5, that's a minus 3. 4 minus 5 is minus 1. 6 minus 5 is 1. 8 minus 5 is 3. 5 minus 5 is 5. Great. Um, when we take the deviation from the mean in the case of the red data set, well, we get 5 minus 5 each time. So we get 0, 0, 0, 0, 0, 0. When we look at the green data set, we get -5 for the first three. 0 minus 5 is -5. And we get +5 for the last three. Great. So these are the deviations from the mean in our examples. And if you want to, uh, we can just say, okay, well, we get a bunch of new numbers here. Let's see, why not, if we're thinking averages give us a good sense of the center of mass or kind of the middle of, in some sense of the numbers we could ask what are the averages of these guys. However, if we look at it, the averages of these guys are actually always going to be 0. So the averages of these guys maybe are not what we want. Instead, what we'll do is we'll square these fellas and we'll take the average of that. So now we're going to take this whole picture and we're going to square it, squared deviations. And what do we get? Well, we get -5 squared is 25. We get 9. We get 1, 1. And this has the effect of making all of our numbers non-negative. So here, if we take 0 squared, we're just going to get 0, no problem. And in the last case, we're just going to get 25, 25, 25, over and over and over again. Great. And now we can take, now if we take the average, we will not get 0. So again, if we took the average of all of these numbers, we get 0. Average of all these numbers, we get 0. Average of all these numbers, we get 0. And in fact, no matter what your data set, if you take the average of the deviations of the means, you're always going to get 0. So you don't want to typically do that. What you do want to do is square them and take the average, and you will not get 0. Not always. So what will you get? Well, we can see that we'll get 9 plus 1 here is 10, plus 25 is 35, and then 35 times 2 is 70. So if we take the average here, we will get 70, and our data set had 6 numbers in it, and so this will give us 70 over 6, which is what is 11 and 2/3 or something around there. Okay, so that's nice. The average for the red is pretty easy to see, is 0. And then the average for the green is also not hard to see because they're all the same number, so the average will be exactly that number, 25. Very good. So this average of the squared deviations has a name, and this is equal to what's called the variance in all cases. So the variance of the data is given by the average of the squared deviations from the mean. So let's define that. The average of squared deviations from the mean is called the variance. Okay. Now, if you wanted a formula, you could write it as follows. So if D1 formula, if your data set is D1, D2, so on to Dn with average A, then your variance, which is often written as V, is equal to, well, you take D1 minus A and you square it. You add D2 minus A and you square it, dot, 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 all the way to Dn minus A and you square it. That's the sum of them. And you take that whole thing and you divide it by n to get the average. So this is the variance. Um, and the variance is a measure of spread. Typically, to get a more useful number in many applications of statistics, it is useful to square root the variance. So the variance is labeled by V, and I'll use that notation V to define the standard deviation. Okay, let's do that. Definition: the standard deviation of a data set is, usually it's denoted by sigma, and it's the square root of V. So this symbol, if you haven't seen it before, is lowercase sigma. Remember that Greek is an alphabet, so it's not all capital letters. There's lowercase as well. And sigma denotes standard deviations is um, uh, square root of V in this case. Okay, so if you wanted to uh, calculate the variance, or sorry, the standard deviation of our three different data sets, we can go ahead and do that. So let's do that here. So the blue sigma is given as the square root of 70 over 6, which is approximately 3.1 or 442. This variance, or sorry, the standard deviation for the red data set is the square root of 0, which is on the nose equal to 0. And the standard deviation for the green set is the square root of 25, which is 5. And what I want to do is I want to explain just very briefly what's going on here. So when all of our data points exactly match up with the mean, in other words, we just have a repetition of the mean, so there's no spread whatsoever, our standard deviation is 0. And that's what you will expect. The standard deviation being very small means that all of the points are very close to the mean. And when we talk about normal distributions, we'll get a better sense as to what very close means. But yeah, a very small sigma, very small standard deviation means that you're clustered very tightly to your average. We see that as they sort of spread out and get a little bit more homogeneous, a little more kind of spread out in an even way, our standard deviation changes to 3.42. But now, if you think about the range of this data set, the range of that data set is 10. And it's equal to the range of this data set. So the range in these two cases are the same. Um, but we're getting a larger standard deviation here because the middle guys are moving out to the side. So in other words, we're getting a larger spread or a larger movement away from the average. The average is farther away from the points in our data set. And that's what sigma detects. It detects that sort of spread away or distance away from the mean. So your deviation should be thought of that way as a way of maybe measuring a type of spread, but maybe measuring like how far are all of the data points kind of viewed simultaneously from the middle, the mean. Okay,